Okay, welcome to the last lecture this season. There are probably new seasons of this type of courses. There are actually many interesting ones which you can see as follow-up courses. So there's I'm going to talk about that in the end of the lectures here, just to point to different directions you can go into. Also for research directions, if you're interested. But what I wanted to do first is to wrap up the discussion we had about the principal component analysis, which we did yesterday, where we went through the mathematics of the method. So the basic takeaway messages for the PCA, principal component analysis, is that we want to maximize the variance. What we did was to calculate the covariance matrix, which is defined by our design matrix, and that contains information about correlations between the different features in our data sets. And then we can use the principal component analysis as a kind of unsupervised method to reduce the dimensionality so that we have a set of effective degrees of freedom. So if you go back to project number 2 and you look at the Wisconsin cancer data, you could now say that I don't want to have all degrees of freedom. I just want to keep something like 5 effective degrees of freedom instead of 30. Now, the way you do this now is to, you can start by diagonalizing your correlation matrix, if you can diagonalize it. And then you would try to maximize the variance, which is the same as minimizing the reconstruction error by keeping only some few components of your features. And for the correlation matrix, or for the design matrix itself, that means that we actually deal with only some of the features which we think are the most relevant ones. And you could try this if you want to in project number 3, if you want to play around a little bit with it. If you have a case with many data, many features, you can easily try to play around by saying that I want to keep a maximum variance of 95% of the total variance. So the total variance is the sum of the variance of all the features. And you would get that by the eigenvalues of the correlation matrix, as we showed yesterday. So the eigenvalues of the correlation matrix give you the variance of the different features. And then if you sum this up, you could say now that I just want to keep 95% of the total variance. And then you can calculate your mean squared error or your accuracy score, and you can see if this is something you would be happy with in order to classify the problem or to make a regression fit to something. So it's an effective way, or if you can diagonalize the matrix, of reducing the dimensionality. If you have huge matrices, there is actually an iterative eigenvalue solver, which is called Langston's method, which belongs to the class of iterative solvers, where the method actually converges to the extremes, the extreme eigenvalues, the smallest one and the largest ones. And that actually fits well this PCA problem because we are targeting the largest eigenvalues, which are then the features with the largest variance. As we saw yesterday, a large variance in your data points meant a large spread, which means also then that you probably cannot compress this data set to a smaller data set. So if you have features with small variance, then we can often try to reduce and take away that feature, as we saw yesterday. And yesterday, before I ended, my Jupyter notebook actually didn't respond, but now it does respond. So I can show you the examples which I was supposed to show at the end yesterday. And the first example which we looked at by setting up the covariance matrix. So we used a very simple example where we then had defined the mean value. So we have 2 features. That means that our design matrix is going to contain 2 columns for the 2 features, and each feature has 10,000 entries. And these are the 10,000 data points. And these are used to calculate the covariance. In this specific case, what we did was simply to say that the covariance, so this will be the first feature has a variance 4, the second has a variance 2, and then there is some correlation between the two features. If this number is very small, it means that there's basically no correlation and we can decouple them. So when you diagonalize this covariance matrix, that would be the eigenvalues of this matrix here. Then when you diagonalize it, then they decorrelate and you have zeros along the non-diagonals. And then the variance is something you would just read off from the diagonal elements. And what we did then was simply to define with that covariance and that mean value, we would simply define a multivariate, since we have two features. We would then define a multivariate normal distribution. And this is a typical way by which you would set it up. Then the next thing we did before we started to do anything was to normalize the data. And the normalization here is typically done by subtracting the mean from each column. So this is the way we prepare the data. You don't need to do that, but it's often done because it's a way to prevent perhaps loss of numerical precision and round-off errors. If you have large variations in your data, this is something which is almost done even if you may not need to do it. So the thing we did then was to subtract the mean values for each column. And this is something you would easily do with pandas. And then you can define the mean value, easily calculated here. And then you subtract it, and then you have a centered matrix. You can scale it. And this is done actually, this is actually the standard scaler, which you have in Scikitlearn, which actually does that for you. So you can then divide by the standard deviation. And then you get scaled and unitless or dimensionless entries, and which is something which also can be useful. So you don't have the hassle with dealing with units. Then you have the centered data, and we set up the matrix to calculate, and we calculate the covariance matrix. This is the centered one. And then what we did next was simply to plot the data points. So think of this as the vector x1 with all its entry, and x0 with all its entries. And in this specific case, the variance is pretty long. There's a pretty big scatter in both directions. So most likely here, since they're also strongly correlated, you may have to keep these features. Now, what we did next yesterday was actually to increase the variance for one of the variables. Then we had a huge scatter and basically no scatter for the other one. And that means that all the points were almost lying on just a straight line. And in that specific case, you could then say that, okay, the feature which has basically zero variance is something which we would leave out. And then continue with just one of the features to describe the data. So the examples which follow here is then to simply show you how you can collect all the steps. So it's easy to write your own PCA program and compare that with the functionality which is included in Scikitlearn. Scikitlearn actually has this. So one of the things we did then was actually to take this example and just calculate the eigenvalues of that matrix you saw, the covariance matrix. So let's just bring it back again. So in this particular case, it's this simple matrix here. And we calculate the eigenvalues. And what we do next is that we print the first eigenvector and we print the second eigenvector for this matrix. And thereafter, what we can do is actually to use the package which you have in Scikitlearn with the PCA. And then you would simply specify now that we have two components. You transform your matrix, which means that what it's doing there, it simply centers the matrix and divides by the standard deviation. And then what I do next is I print out the components of the largest eigenvalue. So here you can see that since you had a matrix with 4 and 2 along the diagonal and 2 on the non-diagonal, you get an eigenvalue, which is 5 something, and another one here. This is the first eigenvector, the component. So you see this is, when you want the probability, you have to square these matrix elements. And you see now also that when you do the PCA decomposition, using Scikit-Learn, you get now the same eigenvector decomposition. This is the eigenvector, the largest eigenvalue. So this code here, as it says here, does not contain all the elements to do the decomposition and reduce the dimensionality, but this is just to check that my own code gives the same as I would get with the Scikit-Learn's PCA implementation. Now, when you do the calculations, so let me just scroll down a little bit. What you would do then is, if we now take this example here, this is an example where we have a 10 times 5 matrix. So we have 5 features. You might think of these columns as features. And then I simply set up a random matrix, normally distributed. I subtract the mean, so I'm doing this centering here. And then I take now my new matrix, center it. I check just the difference between pandas and my own calculation here. And then what I'm doing next here is I'm performing a singular value decomposition, as we discussed yesterday. And then I'm just comparing the matrices which I'm going to deal with. So my matrix now is only going to contain the 2 first components. And you can see now that my matrix has actually been reduced to these numbers here. So this is just a test that I've done the centering correctly. And this would be now my matrix before I've done any kind of PCA calculation, but I performed a singular value decomposition of the matrix. Then you can then do the same thing with remember now that the singular value decomposition, when I kept the 2 first components, the most important components, these are the components with the largest eigenvalues. And these are the components I want to keep. And then you can do the same thing with Scikit-Learn. You now specify that of this matrix here, you want to keep the 2 first components. You transform the data, and then I'm printing the transformed result. And this matrix here should now be the same as the one which I produced myself here. And you will see that that is actually the case when you compare the numbers. There may be some differences in signs, but they all add up properly. So when you fit the PCA transformer to the data set, then you can access the principal components using the components variable. And we will see an example of how you can do that. And let me show you that by an example which you have seen many times now. So this is the cancer data. And in the cancer data, I'm now using logistic regression, just a simple method. And I'm performing now a scaling of the data by the standard scaler, which we have discussed many, many times. I split in test and train as usual. And then I perform my fit with logistic regression, and which you saw from project number 2 actually did a pretty good job. And many people were disappointed by the neural networks that they didn't exceed dramatically logistic regression. So this is a case where if logistic regression works well, you use it. And then you can now decide, and you remember now that the cancer data have 30 features. And now I say that I just want to keep 2 of the features. I take only the 2 first components. So that means that I now transform my train data by the PCA. This is the same as performing a singular value decomposition. So I have actually now rewritten my design matrix, and I keep only 2 components, 2 features. And then you ask yourself, what will the training look like? So the first set here is actually logistic regression, where I'm only trained with an unscaled matrix. And here is actually the training result with the scale data, which is a 99% correct hit. Whereas here, when I now do the PCA data, where I actually reduced the number of features, I get a result which is not that far away from the full logistic regression calculation with the scale data. So that's an example on how you would proceed. But you, if you want to use the full functionality of Scikit-Learn, there is actually something which is a variable here, which you can use, which now allows you to decide how much of the variance you want to keep. So what you could say here now is that you want to keep, let's say, 95% of the total variance. And this is an option which you can plug into the PCA calculation with Scikit-Learn. So what I did in the previous case, I didn't look at the variance. I just said that I just want the two components with the largest eigenvalues, which means the largest variance. And then I had, instead of having 30 features, I went down to 2 features. And then I asked myself, how well does this do in classifying the data? Now, remember now, again, there's an important thing here. We discussed yesterday the PCA, and the PCA is you diagonalizing the correlation matrix. So, sorry, the covariance matrix. If you have 30 features, there should be, when you diagonalize, there should be 30 eigenvectors, each one of them representing one of the features. So when you diagonalize, however, what happens then is that the largest eigenvalues or the different eigenvalues, they will be a linear combination of all the features. So what you would have to look at when you do this analysis of the data, you would actually have to look at the eigenvectors and see which of the features are the most important for the description of a specific feature. Remember now that an eigenvector, when you diagonalize a 30 by 30 matrix, is a linear combination of all the 30 features. And then depending on the coefficient in front of the eigenvector, that tells you which of these features are the most important for describing that specific feature. And ideally, you want it to be the feature itself, but it may have a mixture of other features. But in a way, this is just a way to reduce the dimensionality of the problem. It keeps information of the other features, however. And then you diagonalize, you reduce the dimensionality, you have a new design matrix actually, and then you use that one to perform the fit. You could have decided then to look at the singular values or the eigenvalues and say that you could add an option where you run over the eigenvalues and say that I want to keep 95% of the variance, so the sum of the eigenvalues should give you 95%. That's fully possible. Or you can use Scikit-Learn, where you put this option in the implementation of Scikit-Learn, and that could easily give you, just with a few lines, you can then perform the PCA with a kind of limit here, where you can now set the number of components, and you run PCA again. And this number of components is a float between 0 and 1, indicating the ratio variance you wish to preserve. And this is a very simple way you can implement that. Writing your own code is also equally simple. And as you saw here, as long as you have a code for doing the singular value decomposition, it's very straightforward to write your own PCA code. Now, there are many variants here, and there's one topic which is very interesting, which many people have started to use, which is called randomized PCA. If you're interested, I can give you some links to the literature, and that's often used as a very efficient way of dealing with dimensionality reduction, and it has also smaller computational complexity. You can also use something which is called the incremental PCA, where you actually, instead of using the whole training set to fit the memory, you actually gradually increment your algorithms by splitting the training set into mini batches, and then gradually increment the training sets that way. So this is normally called the incremental PCA. And that's normally useful for large training sets. And also to apply the PCA online is as new instances appear. You may collect new data, and then you would like to rerun things. So there are, for every one of these methods, there are actually tons of textbooks. So everything we have scratched the surface of in this semester, like when we did the support vector machines for 2 weeks, you will find tons of textbooks, and people have dedicated their professional lives to just one of the methods. Similarly here in PCA, there are tons of textbooks on different variants, and PCA was actually one of the very popular methods for dealing with imaging before convolutional neural network came into the game. So singular value decompositions in PCA were some of the standard recipes for dealing with image compression. And you will still find in many of the textbooks, you will find many examples of using the SVD and principal component analysis. And there are tons of other techniques here. Now, one thing which I wanted to do here, before this is going to be the last topic, and I may actually run through with the slides here instead of using the whiteboard. So one of the last methods I wanted to discuss is actually called clustering. And this is a part of unsupervised learning. And the simplest clustering method is a method which is called kmeans. Let me just write down some of these on the whiteboard, because then we break a little bit of the monotony here, instead of just using slides all the time. So let me just bring that up. So the k-means clustering is actually a very simple method to cluster the data into specific groups without you knowing how you should cluster them in different groups. So let me show you the algorithm, because this is also something which is very easy to implement. And you will see examples of this in the Jupyter notebooks of a simple implementation which I wrote some years ago. So the basic idea here, let us write it down here. So this is called k-means clustering. So the basic idea here is, suppose you have a data set. So we have a data set. Set with x0, x1, up to some xn. So we have n observations of a random d-dimensional variables, d-dimensional. So this could be a 2-dimensional, it could be a 1-dimensional, it could be a 3-dimensional, etc. So random d-dimensional variable x. So the goal here is actually to find a partition of the data into some number of clusters. So the goal is to find a partition of the data into clusters into some number of clusters, which we just label as a K. So the way you can think of these clusters in a kind of intuitive way is just as computing a group of data points whose interpoint distances are small compared with the distance to data points in another cluster. So suppose now that you have one cluster here, which I'm just writing like this. So this has a specific position, and then you have a set of points in here. Then you have another cluster here with many observations. So this is cluster 1. This could be cluster 2. And then we have another one here. So these are well separated. So this will cluster 3 and so on. So the idea now is that the distance from the center of the clusters to the points here, so this specific distance, is much smaller than the distance from this point here to a point in a neighboring cluster. So hopefully we can separate the data this specific way by making this kind of clusters. And perhaps these clusters represent some features in the data which we would not have been able to discover if we just went through the whole data set with traditional methods. So the whole idea here is actually to see if there are data points which then can be clustered into groups, and that the distance between these groups of points is much, much smaller than the distance from the points in that specific group to another group. That's the basic message. The algorithm is extremely simple. It's actually so simple that you almost get offended if I present it here. So it's an iterative process by which we can then classify the data points into these different groups. So the way we would do this is to introduce a variable mu of k, which is a kind of a way, if you think of this as a center of each cluster. So think of this as a center of each cluster. So you could think of this being your mu1. This could be your mu2. And this would be your mu3. The goal then is to find, the assignment of points to a given cluster. Of points which then belong to a specific cluster, belonging to a given cluster K. Also, what we want is that the distance between these points and this mu of k is a minimum. So what we end up with doing then is actually to define a cost function which looks as follows. And this is a function we want to minimize. So as I said, the goal is to find the assignment of points belonging to a given cluster, as well as having this mu of k, this center of the cluster, such that the distance of each point, the closest to this mu of k, is a minimum. So that means that we can define a function where we now loop over all the points we have in the data set, n-1, and then we loop over the number of clusters we want to make. So suppose we have k, this is the uppercase k, -1. Then there is a variable ri of k, and this is then multiplied with the norm of the distance between a given point and the midpoint, which we have here. So we would have a midpoint mu of k, and this is just squared here. Now, this r of k is a quantity which takes only two values, 0 and 1. So it's 1 if inside the cluster, if inside cluster, and 0 else. Now, how do we do this? Now, the way we actually solve this problem is to start with a guess. And then we would start with a guess for this mu of k. So we could simply place different, we suppose you have 10 clusters, then you would start with a guess for this mu of k, and then you would start iterating. And this iteration is done in 2 steps. So when we're going to implement an algorithm now, we want to do the following optimization. So first, what we do now is to find an initial value, or just a guess on an initial value. First, select an initial values for this mu of k. Mu of k. Then the next step, which we do here, is then to optimize this function, which means in our case to optimize this c with respect to this Ri of k, keeping this mu of k fixed. So we opt for a certain set of values for this mu of k, and then we start optimizing with respect to r, which is just linear in this equation here. So that's pretty easy to find. Then we do the next thing, the second stage, second part, is then actually to optimize this cost function. In our case, this means again minimizing c with respect to mu of k, while keeping this r of ik fixed. And then you continue till, with these 2 stages, till convergence criterion has been reached, which would typically be that this function c doesn't change by more than a specific amount which you have specified, till convergence criterion has been reached. So if you look at the Rik, this is pretty easy to calculate. So this Rik, when you want to optimize it, we know that that is 1 if this k is equal to the minimization here, argmin, of this distance, xi minus mu of k squared. And this is given for a specific value of j. Oh, sorry, a specific value of I, point I here. And then it's 0 else. And you simply assign the ith data point to the closest cluster center. The optimization of mu of k when r of k has been fixed is also pretty easy, because when we look at mu of k, we have a function which is squared with respect to mu of k. So that means that the derivative with respect to mu of k and driving the cost function to 0, that means that we get 2 times I equals 0, and we have picked a specific value of mu of k. That's why we don't have the sum over the k's. And then we simply get Rik, and this is given by xi minus mu of k, and this has to be equal to 0. So that what that gives us is a mu of k, which is simply the sum over this I of Rik multiplied with x of I, divided by the sum of I of r of ik. And this is just the number of points in a given cluster, in a cluster K. And now you see why this is called k-means, because what we're calculating is the mean value of k with respect to x. So I'm just dividing by the number of events I have in that specific cluster. And this is why it has the name k-means, because this is the mean value of k. Okay? So this is basically the recipe, and it's not that difficult to implement it in this kind of two-stage iterative process. So let's look at how we can actually implement this and look at some examples. Again, Scikitlearn has all this functionality baked in, but it's not that difficult to write your own program for it. You see, you have questions to the algorithm. So it's a pretty easy way. So what we want to do now is simply to create these kind of clusters with a criterion that these clusters here are so defined that the points inside have a much larger distance to the points in another cluster with respect to the distance between the center of the cluster. So let's take a quick look at the Jupyter Notebook again and just switch. And then after that, we're going to take a small break and then try to summarize what we have done this semester. So what you will see in the Jupyter Notebook for this week is actually an implementation of the k-means algorithm. So you would typically, as we start, as I said, we start with guesses, random initializations over k cluster centers. You then, for each centroid, the points that are most similar are identified by the smallest distance. And then you move, replace each centroid with a coordinate average of all the points that were assigned to that centroid. And then you iterate these points 2 and 3 until the centroids no longer move, given some tolerance which you have defined. So the basic mathematics is the one which we put up here, so I won't repeat that. You can go through it, but this is essentially equations. I call this n of k here instead of r of k. And the k-means clustering argument means that you, for given cluster assignments and k cluster means, you minimize the total cluster variance with respect to the cluster means, yielding the means of the currently assigned clusters. And given a current set of k-means, the total cluster variance is minimized by assigning its observation to the closest cluster mean. And then you just keep repeating by optimizing this function here. So when you want to write your own code, what I've done here is actually first to compare also with k, so Scikit-learn has actually a option for that. So here I define a set of points, I define 1,000 points, and I'm going to define points which are scattered according to a Gaussian distribution. I define a mean vector. I define a covariance matrix here, and I use that to define with a covariance matrix. I have a sample variance, which I just input to it. And then I simply define a multivariate normal distribution with a mean matrix and a covariance matrix and the number of points. This is pretty close to what I did in the PCA example, where I defined a matrix of 2 by 2 for the covariance matrix. Then I simply generate some simple data sets, and then I plot it here, as you can see. So this is my model data. This is what it looks like. So this is just a simple, very simple model now, where I've taken a normal distribution, and I'm doing a covariance, a 2 by 2 covariance, and these are scattered all over, depending on the mean value and the variance which I gave to the variables. So you see that there is some kind of scatter here, right? So what I'm going to do now is simply to apply the k-means algorithm and see if I can make some better separations of the data points, because now you see there is a kind of floating between the different areas. There are some chunks of data, and actually when you run an experiment, you may see a situation like that. So we've been analyzing data from nuclear physics experiments, and we wanted to predict whether it was a proton which was emitted or whether there was another charged particle, and they would move differently in magnetic fields. And when you look at the images which are created then, you would get images which can look like this with lots of noise, but then there could be specific traces. And then you want to isolate these events, because in some experiments you can produce many events, and some of them may be overlapping. There may be a lot of noise and junk in addition. So a typical experimental situation may not be so different from that. And then you would like to use some kind of way to, reduce the size of your problem. And this clustering is one way. And then hopefully one cluster has some specific features, another has some other type of specific features, and so on. In this case here, we have just taken a data points and scattered them according to a multivariate normal distribution. Nothing but that. And that you could then generate other types of data. Another question is whether we can use this algorithm and find some kind of other ways of splitting the data. And here I just say that I want to have 4 clusters. And then first I calculate the distance to each centroid in our data. This is this, and then you initialize an array to keep track of to which cluster each point belongs. In this way we set it up here. The index tracks which point and the value which given cluster the point belongs to. So these are just, you can look a little bit more into the details if you want to. And then we can plot it. And the first grouping looks like this. So I've actually had decided that I wanted to have only 4 clusters. And this kind of grouping doesn't look that impressive. Then you can keep iterating. So we have picked k centroids at random from our data points. And they're often, there are other ways of more intelligently choosing the initializations. However, in most of the k clustering, what many people often do is just a random choice of initial values for the number of clusters and also the way you define the center of the clusters. So we then initialize an array distance, which holds information on the distance or dissimilarity of every point or centroid. And finally, we initialize an array cluster labels, which according to a distances array holds the information of to which centroid every point is assigned. Then you can continue now, and you can say that, okay, let me do 100 iterations. And then I set up a tolerance so that when this tolerance has been reached, then I would stop my iterations. And in this case here, I'm simply implementing the kmeans algorithm. This is nothing but that. And you can go back to the equations and take a look at the way the code is set up here. And then when you plot it, so this actually after 5 iterations have converged, and then it would look like this, which looks more reasonable, right? So now I made a clustering and the points belong to specific clusters. And then you could ask yourself, what do these clusters mean? So the algorithm is extremely simple to implement. And I would say very intuitive. And this is also the reason why in many, many cases, if you don't know how to extract information from your data using traditional algorithms, using k-means clustering is a very simple way of perhaps, if you're lucky, to find some patterns. And this means that if you look at your data set now, you have much less data points in a small domain. And perhaps then you can do PCA in each domain to reduce the dimensionality further without you dealing with all the dimensionalities. Or you could say, now I have a much more reduced data set. Let me now apply my neural network classifier to each of these clusters and see if I can actually then tell something about what this is and how it behaves. So k-means clustering is a way actually to prepare for a data analysis with more labeled methods. Because now you would say that this specific cluster number 1 may belong to some specific features. So when we did this analysis of the nuclear physics decays, then we could recognize that each cluster belonged to a specific particle decay. And with that, we could then start doing the analysis with traditional label methods because each cluster would then correspond to a specific event. So it's a very easy and extremely useful way of partitioning your data. And then depending if you're dealing with images, some of these images may be easily recognized as this and this type of events. So you would actually then have a cluster of data which you can label as that specific event. So this is going to be the last method. So we use this week to actually discuss unsupervised learning. And the methods which we have dealt with are some of the most popular ones, PCA and kmeans clustering. But there are, as you may realize or may imagine, there are tons of many other methods for unsupervised learning. So this course is mainly about supervised learning. Yeah. No, it wouldn't do that. It wouldn't be able. So there could be outliers in there, but this is something you would have to look at in the post-analysis of the clusters, whether there are events there which should not belong to that cluster. So in many experimental situations, you have lots of noise, and that can easily confound the clustering analysis. But the hope then is that by reducing the dimensionality of the problem, you can then treat that with traditional methods, whether these are you looking at the data, because you have a reduced set of images you want to look at, or having an algorithm which goes through, let's say, some image recognition. So after the break, I just wanted to summarize a little bit and discuss what we have done. And we could also, if you guys want to, we could say something about project number 3 as well. And then we're going to wrap up and finalize. So I'm going to put the recording to pause. And then we start after the break with a kind of summary of what we have been doing this semester. Holding here. So this is this last session here is just a kind of us summarizing what we have done. And as you probably have seen, if you looked into the slides for this week, there's this image which I always been very fond of, because that reminds me of myself before the exams. So I tended to procrastinate a lot. And then I would just be in this happy situation 1 week before exams. And then 2 days before, it's in the middle one. And the final day, you don't remember anything. So in a way, the hope here is that we avoid, by having projects, we avoid this hassle with you in a way almost gulping up what you have done, and that you have had a possibility to gain more insights about the methods by actually working on projects, and which is also something which allows people to take a kind of ownership of what is being done, and that it has given you flexibility to do research and explore things. What I wanted to say is more to bring in some perspectives. And we have, the way we have defined machine learning, so machine learning is often seen as, so artificial intelligence is actually seen as a set of methods to do, or set of machine learning algorithms to solve specific problems. But artificial intelligence can also be done without machine learning methods. So that's actually a big field of research. So many people often tend to mix artificial intelligence and machine learning. So the way we would define artificial intelligence in this course would be as a collection of machine learning methods used to solve a specific task. But you can have artificial intelligence without machine learning. And what I've done here is actually to put up various links. And if you have time, just take a look at some of these links, because they often provide interesting discussions and interesting perspectives, which I haven't covered. So hopefully you may find something inspiring when you look at these links. And if you go back to the beginning of the semester, when we set out with different learning outcomes and so on, and we define machine learning, what the focus here has been on you being able to fit a function or fit some properties and then find correlations in the data sets. And This normally defines what we might call traditional machine learning. However, what is more interesting is actually to be able to combine traditional machine learning with normally what's called Bayesian statistics, where you are interested in predictions, correlations, estimations of errors, and causation. So what is the probability of B given A? So Bayesian machine learning is actually a very interesting field of research. And what we have typically looked at here is to develop algorithms that can find patterns in a data set in some kind of automatic way. But we have put less in emphasis on making error estimates, which requires that you have a probability distribution. We've seen some of it when we looked at the interpretation of ridge and lasso regression from a probabilistic point of view. And that's where we used Bayes' theorem in the beginning of the semester. However, when you look at many of the methods which we have looked at, this kind of more frequentist approach, where we start with the frequency of the data, you can infer a probability distribution. But we have methods like Gaussian processes and Bayesian statistics, where we often try to assign probabilities to specific events. And that probability represents some kind of measure of belief, confidence for that event. And the belief can then be updated in the light of new evidence. So there is a strong push towards bringing together standard machine learning, which is more about predictions and correlations, and Bayesian statistics. We have a field like Bayesian machine learning, where you try to merge together predictions and correlations with estimations of errors and causations. So what we have done this year is basically to look at two main topics. We have looked at the optimization of the data, and we have looked at specific machine learning methods. So the statistical analysis are things which we did with Bootstrap, with cross-validation. The optimization is actually the optimal calculation of gradients. This is something we spend time on, and you spend time on that on project 2, which is really the bottleneck. And if you look at the topics here, you may ask how much of this we actually covered and how much of this you may remember that we have done during the semester. But ideally, these are topics which we wanted to cover. We actually put less emphasis on specific distributions, although many of you have not had much statistics in your bachelor degrees. We've been looking at singular value decomposition, matrix inversion. Gradient methods are extremely important. We have been looking at estimation of errors, cross-validation, Bootstrap in particular, and then also practical optimizations using a singular value decomposition. And then now, recently, we did the principal component analysis in order to reduce the number of features. So the methods which we have looked at throughout the semester are basically so-called supervised learning methods. So we've been doing these regression and classification methods, linear methods, and you recognize the names. We've been looking at neural networks and deep learning. And then we looked at decision trees. We've been looking at support vector machines. These are the 4 main sets of methods which we have looked at. Linear regression and linear classification, which led to logistic regression. 3 central methods in deep learning. And then we have the trees and ensemble methods, which are widely popular and extremely easy to implement. So many of you actually in project number 3, you're planning to deal with the boosting methods and compare those with neural networks as you did in project number 2. And boosting methods often are methods which are extremely popular when it comes to classification. And then we have the support vector machines, which are also very popular methods. And if you now look at what we have tried to do during the semester, besides writing projects and other things, so the projects are actually the central themes in the course. And these are the things which we hope you actually have been able to extract from this semester. So understanding linear methods and regressions and classification, learn about deep learning, ensemble methods and decision trees, basic data analysis. We haven't put that much emphasis on it, but it's been there all the time in the different projects. And then to have an understanding of central algorithms. So the algorithms we have looked at, these are central algorithms in supervised learning. And hopefully they can serve as a kind of platform for diving into other more advanced methods in the next semesters. So you will see later a list of different methods which we have looked at. So I'd say I am pretty biased when I'm saying this, but this is a field which has increased dramatically. So let me just give you an example. There's a popular preprint server for many fields in natural science, which is called ArcSieve. Have you heard of that? Many of you seem to be nodding. So ArcSieve, A-R-X-I-V, there you will find preprints in physics, in mathematics, machine learning, finance, bioscience, etc., etc., etc. So it's the main preprint server. And if you are not familiar with it, let me just bring it up here. And then you can see the kind of diversity which you have. So if you're dealing with, so it started with my own field, subatomic physics, particle and nuclear physics. And then it has mathematics, computer science, quantitative biology, quantitative finance, statistics, electrical engineering, economics. So when you before you publish papers, you often place your preprint here. So, and if you go to computer science, you will actually find there should be one actually on machine learning here, right? And typically what you would find then would be the recent submissions, and you will see there are pretty many. So this is today's, just the submissions today. And it has actually a service here where you can find how many papers have machine learning in the abstract year by year. So in 2015, there were 800 papers submitted here which had machine learning. Till now in 2022, there are 12,000. That says everything. So it's within 7 years, there are 10 times as many scientific papers which have the word machine learning in the abstract. And in total, this database, which was established in the beginning of the 90s, has something like 1 million scientific articles in total, 1.5 million in total. So machine learning is really a field which has exploded, and you will find applications of machine learning everywhere. Some of the resources, you can follow this on ArcSieve. You will find many new papers. It's a journal of machine learning. There are tons of new papers coming up and new journals on machine learning. If you start looking at machine learning, if you want to summarize a little bit and you want to decide what kind of method to use, you have to identify whether you have a classification or regression problem. These are pretty obvious things to you guys now. You consider your data carefully. That's a very important aspect. So in many of the examples we have looked at, we have had simple data sets, or we have been using Scikitlearn's database. So we like the cancer data and other data sets are already included. So the data have already been prepared for you. You can immediately extract the design matrix. But you only have other data sets where you have to set up the design matrix properly. So in the beginning, you choose the simplest possible model. There is no reason to overcomplicate in the beginning. And then you consider your data carefully again, think of data representation more carefully, And based on your results, you have a feedback loop to the earliest possible point. And then you have to choose a model, supervised. This is what we have dealt with mainly. Again, start with the simplest model that fits your problem and start with a minimal processing of data. And then you can gradually increase with more and more data if you can. You should shuffle your data, mean center. We've been discussing that up and down again. It's not always needed. You may normalize the variance. This is often done. And one of the reasons is that you want to have dimensionless results and you want to get rid of units. It's pretty common. You can decorrelate data. So PCA is actually one way to decorrelate the data with a singular value decomposition where you diagonalize the correlation matrix. And then you also have to decide when you want to do the train test validation splitting. So whitening is something which is also a decorrelation transformation that transforms a set of variables, random, into a set of new random variables with identity covariance, uncorrelated with unit variances. This is something which is done sometimes. We haven't put that much emphasis on it. And then when you deal with neural networks, you have all this pain with activation functions. Which one should I use? ReLU, HeLU, sigmoid. How do I initialize the weights? Should you set all weights to random values, etc., etc. So these are probably things which you all have done and tried. So you cannot set them to 0, obviously. There would be no training. That's a pretty bad idea. And these are many of these kind of tricks of the trade, where you hopefully have gained some additional insights. And then we have all the thing which disappoints people so much, that there's a tons of parameters which you can tune. In the stochastic gradient, we have stochastic gradient descent plus momentum. You can do a plane gradient descent with momentum. You can have state-of-the-art approaches to update the learning rate, like the root mean square propagation, ADA-grad, ADAM, and so on. And then the question is which regularization and hyperparameters you want to use. So there are many of these things which you need to explore when you run a machine learning algorithm, especially if you do deep learning. All these parameters become parameters you would have to explore in order to find the best possible representation of your data. Then we have resample. So we've been paying attention mostly to bootstrap and cross-validation. And cross-validation is the kind of more standard method. And it has to do with the fact that doing a cross-validation on, let's say, k from 5 to 10 folds is normally computationally cheaper than doing a bootstrap many, many times. So cross-validation tends to be the method of choice. And in many of the choices which you see, there is you striking a balance between how much time you're willing to wait and how many cycles you're willing to use and the accuracy you're willing to accept. So this is a kind of balance you have to strike. So somehow you have to decide, okay, I'm happy with what I have. This is the best I can get out of this data set with these methods. Now, what I wanted to point to is actually courses which you may find relevant. So we've had, and many of you have actually taken this IN 4050, but we have one on natural language processing. I think that's going to be discontinued. But we have this course here, which runs in parallel with this course, which often goes a little bit more into the deeper, into the statistical analysis. So this is a fall semester course, this SDK, the IN 4300. So this is normally tailored to students with more interest in mathematics and the statistics of machine learning. It doesn't cover deep learning methods. It has, because the guy who teaches this course is actually an expert on boosting and gradient boosting methods. So there will be a lot of boosting. Then we have some other courses here. We have this IN 5400, which we normally tend to recommend. If you are interested in imaging and machine learning, IN 5400 is a typical course which many take in the spring semester. And this is an excellent course, and it puts emphasis on methods which we have been sloppy with, like convolutional neural networks. We haven't written a code about that, but we've gone through the essential mathematics, but we haven't gone into the gritty, nitty details. And it puts also emphasis on reinforcement learning, more advanced deep learning methods like generalized adversarial networks, autoencoders, and so on. So that course is a course which I normally recommend when you've taken this one, because they cover neural networks in just one lecture. And then they do the standard basic regression, which we spent almost a month on. They do that in just another lecture. So having done this course brings you quickly up to speed with what they cover there. There are other courses as well. And there are courses in statistics, which I normally recommend. So there's actually this one, which is called Bayesian analysis, which is very useful if you want to look at this perspective, which combines machine learning with Bayesian statistics. And that's extremely useful. There's also, for those of you interested, there's a new course now, which is called FYS 5.4. This is a self-study course, but this is called now, let's put it in English here. It's called Advanced Machine Learning and Data Analysis for the Physical Sciences. This is a course which is based upon this one. But this is a self-study course. Okay, let me just bring back this. So these are examples of courses. So if we now want to go into the more, how to say, speculative corner, or no, sorry, speculative, this is actually happening. What you might say is that if you look at the progress which has taken place in deep learning methods and how these algorithms have been modified and developed in the last few years, they're actually huge progress when it comes to things like convolutional neural networks, recurrent neural networks, encoder-decoder framework. And these are methods which are, if you go into this ArXiv website, which I showed you, you will see tons of new articles, almost on a daily basis, which address various aspects of deep learning methods. And clearly, these are methods which we haven't discussed in that big detail in this course. And that's obvious, by obvious reasons, because we don't want to have a credit overlap with, let's say, IN 5400. And there's also a limit to how much we can squeeze in to 10 credits. I'm not going to say so much about this. We've been looking at classification, regression, and we barely scratched the surface of clustering. And we've been mainly looking at supervised learning. We haven't said anything about reinforcement learning. This is covered by this IN 5400. They actually have 2 or 3 weeks dedicated to reinforcement learning, if you're interested in that. So it's a course which many people are interested in taking. And I recommend it. I'm going to skip this with Boltzmann machines, because Boltzmann machines were extremely popular before convolutional neural networks really started to rule the ground. And they have basically wiped away the interest in Boltzmann machines. As with the imaging, where PCA and the singular value decomposition were some of the dominating methods, with the CNNs and these huge data sets like ImageNet and so on, they are just being used now as a kind of defaults for image recognition. But we have things like autoencoders, which is actually a very interesting technique. And I invite you just to take a look at some of the slides if you want to. I have tried to link up with the videos on the different topics. And many of you may encounter in your research these more advanced topics. So this course was in a way a kind of you giving the overview of some of the basics. And then hopefully you may find an interest in more specialized topics later, which may be useful to your research here. So I'm not going to say so much about these things. Bayesian machine learning is actually a very hot topic. So you can now, so the essence of that, if you think of neural networks, you're going to train a probability to define your activation function. So instead of having your ReLU, sigmoid, and so on, you actually develop a probability distribution for the activation functions, so that then you spit out a result with a given probability. But you can quickly see that this is going to take a lot of time. So Bayesian machine learning becomes extremely expensive from a computational point of view. So it's going to replace you having a fixed activation function with a probability distribution, but it has a drawback, but it's computationally inefficient. It's elegant and nice, but there is a lot of research in these directions. There's also a set of slides here if you want to look at it. And it allows us to encode our prior beliefs about what those models should look like, independent of what the data tells us. And that's especially useful when you don't have a ton of data to confidently learn our model. So keep in mind, the reason why I bring this up is that all the methods we have been looking at are data greedy. So neural network, the more you can feed in, the better the training. And you saw that in project 1, when you were looking at the bias variance trade-off, that when you change the amount of data, your bias variance trade-off would improve. If you have few data and did the training, you could quickly get a variance which exploded and you ended into overfitting. So everything we have done is essentially a data greedy method. And when you have a probability distribution, then if you can define it, that's a way for you to produce new data. So what you will often see in basic research is that we may have a limited data set. And when you then define a probability for generating these or that data point, what you would do then is to use that to generate new data. So you can augment the lack of experimental data with theoretical predictions. And then you can train a model, you can make the model more data rich, and then you can try to train a neural network on a set of data which contain experimental data and theoretical simulations. So this is often something which is done. So people would typically combine many different types of methods. Reinforcement learning is a hot topic and is perhaps one of the more exciting ideas, which we haven't covered at all. And this is something which you will encounter in a course like IN 5400. And it's been around since the 50s. It's been producing many interesting applications. One of them is something you may have heard of, the AlphaGo. This board game would actually bait one of the best players in the world. And again, I put in some videos here. And there's also this textbook by Aurélien Géron. And chapter 16 has a very nice discussion and hands-on application of reinforcement learning. Now, transfer learning, I'm not going to discuss everything. Adversarial learning is actually quite interesting. So the model tends to generate extreme instances to maximize the probabilistic likelihood. It utilizes adversarial behaviors, generating adversarial instances, so training an adversarial model to enhance the robustness of the model. There's a whole field here in technologies on supervised learning in particular with generative adversarial networks. And they have been very successfully applied to image, speech, and text. And again, there is a video here if you want to take a closer look at it. I'm not going to say everything which you have here. There's a lot of stuff which I plugged in. You can just take a look at it. So one of the challenges which is facing machine learning, so if you look at the mainstream machine learning technologies, typically seen as black boxes, and people are actually concerned about their potential risks. We may want to make machine learning more explainable and controllable. However, the computational complexity is usually very high, and we may want to invent lightweight algorithms implementations. In many domains, such as physics, chemistry, biology, social science, people usually seek elegantly simple questions to uncover the underlying laws behind various phenomena. And in the field of machine learning, the question is then, how can we extract something simple from, let's say, a neural network? So if you look back at project 1, you fitted a polynomial. And that's something which is easy to explain at a cocktail party, right? This data follows this and this polynomial. Then you do a neural network, you just get tons of parameters, weights and biases, which fit and try to do the best representation of that function. And then it's very difficult to just extract a simple understanding of what is fitting. However, if you believe that your neural network has given the best solution, then you can start to study other quantities with that fit, and then try to extract some simple messages. So in my case, I'm using this to solve quantum mechanical problems. And when I have a neural network, I cannot go back and say that this has this and this simple solution, but I can calculate other quantities from which I can extract a kind of insight about what the network has given me. So that means that you have ways to interpret the data. But a neural network just gives you the weights and the biases, and it's not that it gives you a simple explanation, it's due to this and this. You would have to interpret the data. And that's possible, but it needs that you having a more deeper insight about the data you want to analyze. And there's a lot of things which people also have used, many of these machine learning methods. That's actually to extract, for example, physical laws from data. So you can actually look at data positions of planets to extract Newton's gravitational law. That is something which has been done by actually several groups. And there's an interesting article here on physics from data. If physics is your field, if that happens to be the case. My hope, however, if you look at this point here, is that you don't see machine learning as black boxes anymore. So the basic philosophy, the red thread of this course, has actually been to explain the algorithms. And at the end, what you see is that there is actually a human who writes the codes. And the human has to put in the if tests, whether you accept the solution or not. So sometimes there's a big hype that actually this is something which the machine would take over and just do for us. But actually you have to still, we have to actually write the codes, we have to make the decisions, and we have to make the interpretations. So there's still space for us. I think there's going to be space for us all the time. This is a little bit repeat of what I mentioned about Bayesian machine learning. There is in many cases, we want to extract more than just predictions and correlations. We want to say something about causation. And that's where Bayesian machine learning is an exciting research direction nowadays. So that you, in many fields, you want to have both a probability and you also want to fit the data. And the probability is extremely useful in order to make predictions of things which you perhaps cannot measure in an experiment. There's another field which, and I invite you to take a look at this. This is pretty hot. So it's called, actually the title of this scientific article is called Applications and Techniques for Fast Machine Learning in Science. So this combines active use of hardware development and software development for scientific discoveries. So in particular, in a field like accelerator physics. I'm coming back to physics because I am a physicist. You can actually tune the beam by using machine learning methods, so you can change the quality of the beam on the fly. And that involves both hardware adjustments and also software developments, which can allow you to do that. So in that article, there are several examples on how you actually can use this topic of fast machine learning across a number of scientific areas. Techniques for training and implementing performant and resource-efficient algorithms, and computing architectures for implementing these algorithms. So it's there are several examples there from a whole broad spectrum of scientific fields where there's a huge development going on, particularly in bioscience and in genetics. This is a top research field. And these are typically multidisciplinary fields of research. I'm going to leave this out. Quantum machine learning is one of my hobby horses, but I'm going to say something about a topic which many of you may find interesting, is actually into applications of machine learning into humanities, social sciences. So it's actually pervading many, many fields. And you will find that, for instance, we had a big project with political science, because if you look at the EU, when you write the law texts, they are originally drafted in the leading languages, which would typically be French, German or English, Spanish. And then they often translated then to, let's say, Bulgarian, Greek, and so on, the minor languages, right? And then you have to ensure that the meaning of the text complies with the meaning of the text which was written in, say, French. And then people have actually used machine learning on text to make sure that the meaning is not lost in the translation. That's a typical application of a large machine learning project on text analysis. And people in the humanities, they often use that quite a lot. If you have zillions of pages you want to go through, clearly you won't sit there evening after evening reading these pages to find specific keywords, right? Perhaps the last word. I like this quote here: the best way to predict the future is to create it. I think the nice thing with machine learning now, it's still in this kind of, I shouldn't say embryonic phase, because it's a pretty mature field. But some few years ago, nobody believed in it, not much. But it's a field which is extremely creative. There's a lot of space for new efforts, new ideas. And at the same time, it's a field which is not that set yet. So there's a lot of fluidity and a lot of ideas floating around, and it's driven by people your age. That's also very important. And finally, if you want something to read when the break kicks in, there's actually a very nice book, which is more critical about AI. And anything from, in that book, I learned that Elon Musk is not a car producer. Elon Musk is a smart guy who has seized control over 50% of the world's lithium resources. So making batteries is Elon Musk, not Tesla. I didn't know that. And extracting lithium hydroxide is an environmentally horrible thing. The lithium mines are just, after they have been abandoned, they're just a wasteland for millennia. So there are many, many interesting implications and ethical aspects. Like you probably, I don't know if you remember, there's an American company called Palantir, which has specialized on facial recognitions. And they actually, during these sad moments we are going through now due to the war, they actually sent to Russians use face recognition algorithms to target parents in Russia with dead Russian soldiers. So that's, yeah. And this company has also specialized on facial recognitions, which can be used to manipulate you know, how you can use facial recognition in things which we may not be too happy with. You can take a look at this, and then you can take a look at some of these wordings here. You may agree or not, that some of them are very, how to say, like the one by Woody Bledsoe, number 3 here. In the long run, AI is the only science. So some of them are pretty, I'll say, sharpened, or like there's a popular textbook where it says relevant to any intellectual task. It is truly a universal field. You may discuss you may argue against the pros and cons of some of these arguments, but there's a field which is extremely broad and very, very interesting. And in many disciplines now, we have so much data that it's very unlikely that you will sit and go through every single data which you have. So many of these operations have to be automatized anyway. So this deluge of data is something which we actually have to think of automatizing. Okay, this concludes my inputs to you this semester. And it's always sad when the semester is over, but it's been a great pleasure to get to know you all. And best wishes with exams and everything and the rest of your studies. Take care, guys. Right? Okay. And by the way, I'm going to send you